start. We have main engine start. 4, 3, 2, 1, 0, and liftoff. Liftoff of the space.
In our natural pursuit of knowledge, space has always mystified and beguiled us. Over the past 5 decades, we've pushed the final frontier inevitably onward into the ether. The cost has been colossal. Now every day, new data, new conclusions, and the thirst for deeper exploration propel us inexorably onward. The advantages of the discoveries made through space travel are myriad, but the fundamental curiosity as to what is out there will always fascinate and taunt us. Come with us now into the unknown and discover the disappearing frontier. Coming up in this edition, in the 17th century, Galileo turned his telescope on the sun and recorded how its surface constantly changed. Today we're learning more and more that eruptions on the sun can affect the Earth in many, many ways. The Landsat satellite opened up a new era of Earth resource management, using the technology of the space age in the quest for more and better information about the Earth's environment. Weather and climatic changes, atmospheric pollution and disturbances of the ozone layer, worldwide magnetic storms that disrupt radio and radar, telephone communications, and even cause power failure. All these may well be controlled by eruptions on the sun, which affects Earth's magnetism and creates the auroras by means of a vast engine around the Earth, the magnetosphere. Because this magnetosphere can affect the Earth in so many ways, understanding how it works might help us cope with climate and pollution variations, and even help us in planning our food and energy resources. But how can we start to understand the magnetosphere? In 1600, William Gilbert told us the Earth was a great magnet extending into space. 10 years later, Galileo turned his telescope on the sun and recorded how its surface constantly changed. But then for 300 years, the Sun and Earth pursued their courses, and no convincing theory was able to connect Galileo's solar changes with Gilbert's terrestrial magnetism. Until a solar theory in 1890 suggested the Sun throws out particles which travel to the Earth to be caught in its magnetism. In the 1950s, the Sun's own magnetism, it was suggested, flowed into space to envelop the Earth and generate the auroras high in the terrestrial sky. Of course, this was only speculation on how the Sun might affect the Earth through an invisible magnetosphere. Only to be getting an accurate measurement in space could the true facts be unearthed. In the late 20s, Goddard, the American, built the first practical rocket craft. The Russian Sputnik was the first space success. The American Explorer soon followed, carrying with it a Geiger counter. Signals produced by the counter enabled Dr. James Van Allen to confirm that he was recording something real but unexpected in space. It turned out to be the first discovery in space. The Van Allen radiation belts, particles invisible to the eye, which came perhaps from the Sun, were trapped in the space around the Earth by the planet's magnetism. This was the first step in establishing the link between the Sun and the Earth through the magnetosphere. The first concept of the magnetosphere was that of a region where Earth held particles that were captured from the Sun. But did these particles really come from the Sun? To find out, instruments had to be fired further out into space to really discover if the erupting surface of the Sun did throw out particles and magnetism all the way to the Earth. And from space, this answer came back. Streams of particles flowed from the Sun, dragging out the Sun's magnetism, solar wind rushing into space. But Earth's magnetism in the magnetosphere deflected the solar wind around the Earth. So how then could the solar particles get in and be caught? Solving this space problem could be difficult. Researchers discovered that by going above the Earth's poles, solar particles could be detected entering directly into the Earth's magnetosphere, while within the magnetosphere, further measurements showed that what was also invisible to the eye, seas of plasma particles around the Earth, and huge particle streams moving thousands of miles back from the tail, perhaps to directly ignite the brightest auroras. But what could drive the magnetosphere into these vast movements? Could the solar wind, rushing past outside the magnetosphere, supply the energy? One theory hinged on a magnetic connection, magnetism from the Sun connecting with and dragging back Earth's magnetism. This would work like a dynamo in space, transferring energy into the magnetosphere, where it's stored until suddenly released in a magnetic storm to disturb the Earth and create auroras. But such auroras appeared to be created when stored energy was released in a violent eruption throughout the magnetosphere. But where could proof of this be found? One place is the Arctic, for auroras can be seen almost every night. So scientists searched for clues to show how the magnetosphere collected energy from the Sun, stored it, and suddenly released it to the Earth, creating auroras in a burst of energy equal to that of a large earthquake. So analysis concentrated on finding how the magnetosphere worked and, in particular, what triggered its energy releases. Could it be changes in the solar wind? To scientists, it seemed that changes on the Sun, which changed the solar wind, appeared to trigger an energy-filled magnetosphere into a sudden spasm, creating a magnetic storm, the brightest auroras, and affecting the whole Earth environment. Investigations continued. This is a computer simulation of the Earth and auroras from space. It was part of an experiment to measure exactly how magnetosphere energy creates them. And beyond that, there were active experiments. Canada, radio signals which disturbed the magnetosphere were received from the opposite hemisphere of the world, the Antarctic. The signals received from the South Polar region arced through the magnetosphere to supply a record of the changes that were happening there. The most active experiments were carried by man in space on the space shuttle. To help them understand space, scientists developed laboratory simulations of a magnetic Earth and the solar winds streaming at it, and were able to produce a visible representation of the magnetosphere. But the picture was blurred and out of scale. Only space measurements would be valid in constructing a true diagram of a magnetosphere and its movements. Simplified images of this complex engine in Earth's space showed activity in what, until that time, there was thought to be only empty stillness. These images were a gauge of the understanding of those pioneer researchers and their ability to predict how changes on the Sun would, in some ways, affect the magnetosphere and the Earth environment. At forecast centers, it became standard procedure for the Sun to be kept under watch around the clock. Scientists realized that the magnetosphere was a complex engine through which the Sun caused enormous disturbances to the Earth's environment. They knew that by discovering all the details of how the magnetosphere worked, they would be better able to predict its effect on the atmosphere and its influence on short and long-term weather patterns, and on changes in the Earth's ozone layer. It proved to be crucial research for mankind. Ecology, the balance of nature, is important to all life. One of the tools we can use to monitor this balance of nature on Earth is the satellite. Satellites can be used to observe our planet from a high vantage point. From far out in space, the Earth appears serene and beautiful, displaying no hint of our crowded planet's many problems. As we've used and changed our planet, we've become aware in many ways that we are exhausting our food supplies, our sources of energy, our natural lands, exhausting the potential of the once seemingly limitless oceans. Management of Earth resources is at a critical stage. It's never been more important that we understand the environmental relationships of our planet. Scientists have, for many years, been striving to apply the technology of the space age, the quest for more and better information about these complex relationships. In 1972, a new kind of satellite left the launch pad and rose to an altitude of 910 kilometers from Earth. There it settled in a circular orbit around the planet. This satellite, called Landsat, opened a new era of Earth resource management. Landsat's recordings of the Earth's surface are not photographs as we usually think of them. They are images formed using the techniques of remote sensing, that is, sensing from a distance. We're all familiar with remote sensing. You're using a remote sensor to view this video. Landsat uses another kind of sensor, an oscillating mirror, which captures the light reflected from the Earth's surface. Different areas of the Earth's surface reflect varying amounts of light. The oscillating mirror of Landsat's multi-spectral scanner reflects light reflected from the surface of the Earth to 4 sets of sensors inside the satellite. Each of these 4 sets of sensors is sensitive to a different wavelength of light. Light, as perceived by our eyes, is only part of the electromagnetic spectrum. Other parts of this spectrum include ultraviolet light and infrared light. Landsat was sensitive to the red and green bands of light in the visible spectrum and to 2 infrared bands. These are the wavelengths of light called spectral bands, which were used to create Landsat's unique images. An astronaut can bring back film when he returns to Earth, but Landsat, which was designed to orbit for years, could not. Instead, it transmitted signals which were used to form images. Landsat's oscillating mirror scanned the ground and received light from small areas called picture elements or pixels. Each pixel was 1.1 acres, approximately the size shown here. Landsat received the light reflected by a pixel. Sensors inside the satellite give the light a number between 0 and 63. Bright areas receive high numbers. Areas with less reflectance receive lower numbers. Each area of the Earth is seen as a pattern of lights and darks, coded with numerical values in each spectral band. Landsat sent those numbers to receiving stations on Earth, where technicians recorded them for future use. The numerical information was received and stored on tape, which was then used to make images on film. There were over 7 million pixels in a Landsat image. Remember, the amount of light reflected by each pixel was given a numerical value. Those numbers, one for each pixel, were then converted to the blacks, whites and greys of the Landsat image. This process happened simultaneously in each of the 4 spectral bands, producing 4 black and white images of the same scene. At any given point in an image, the reflectance value was different in each of the 4 spectral bands. For example, the outlined area, a redwood forest, might vary in reflectance from 15 to 35. By combining the separate black and white images and printing them through color filters, the differences in them could be used to emphasize specific Earth features. But the colors weren't normal. Vegetation, for example, was seen as red. For many uses, these photographic products of Landsat data were a great advancement over any other form of aerial surveillance. There was, however, one disadvantage. Researchers were unable to display each individual pixel. They overcame the difficulty by experimenting with a digital computer. The cursor was used to train the computer on a particular theme that required analysis, in this case, the sediment emptying into the ocean from a river. Having done that, they could then display all similar areas of sedimentation in the image. The Landsat views offered researchers one totally new service. The satellite orbited in such a way that it always passed over the same area at the same time of day, recording exactly the same spot on Earth once every 18 days. This repetitive coverage provided an ideal tool for monitoring changes on the Earth. For example, note how well these images of Washington, D.C. show seasonal changes. The bright reds denote the healthy vegetation of spring and summer. The edge of a snowfall is clearly defined on the winter image. Landsat images contained a wealth of detailed information. Some of it obvious, but much of it very subtle. These images provide raw material to be studied and interpreted by people engaged in many kinds of research. The images played a major role in allowing botanists to map America's Great Dismal Swamp, covering an area of 125,000 acres. The swamp was one of the eastern seaboard's last remaining wild lands. The terrain, the water, and not to mention the bugs and insects, made it virtually impossible for the scientists to gain an accurate map of the region. When accessing the Landsat images of the swamp, certain features were easily located. Lake Drummond in the center of the swamp stood out clearly. Cleared areas showed up distinctly, such as an area cleared by a lightning fire. Not all the features were so obvious. One area of the computer-generated scene puzzled the scientists. It showed up as evergreen, but different from the evergreens that had been previously mapped. After forging their way into the dense undergrowth to physically check out that area of the swamp, the botanists discovered that Landsat had identified a beautiful cedar forest. Another product of the research at the Great Dismal Swamp was an ongoing thematic map of the area showing plant associations. Having a base map based on the Landsat images would allow comparisons with new Landsat images each year in order to monitor changes that took place in the swamp. Landsat imagery was made available to anyone from any nation. The Eros Data Center in Sioux Falls, South Dakota, distributed images and tapes to people all over the world. Landsat images provided new sources of information about many different kinds of Earth resources. The satellite was used to map the extent of flood damage. Landsat's before and after images played an important role in determining how fast water recedes and damaged land recovers. Landsat kept track of land development, for example, how well areas damaged by strip mining were reclaimed. Scientists used Landsat to map remote areas as possible wildlife habitats, to search the Earth's surface for clues to new mineral deposits, to inventory the world's agricultural crops so that food and fiber resources could be better managed. Future geography books were able to use Landsat images to show the world as it really is. This map, made up of 569 separate Landsat images, carefully pieced together, gave a dramatic view of the United States that had never before been available. Perhaps it was Landsat's beautiful views of the Earth that impressed on all who saw them that the Earth is indeed a wonderful treasure. That brings us to the end of this edition. We look forward to your company next time. But remember, we are out there. What we can and can't see is out there, and the mysteries between us, although seemingly insurmountable, are encompassed by a disappearing frontier.